Hello everyone. Good morning, respected Dr. Paresh Patel sir, Khushbu Desai madam, beloved lecturers, and all the participants. My heartiest welcome to Dr. Paresh Patel sir, our honorable speaker of the topic Symmetry and Group Theory and its application in chemistry. Dear participants, so far we have reached the third session on this topic, and we have learned a lot from Sir. Sir has delivered very expertise knowledge on the topic. I would like to request Dr. Paresh Patel sir to continue with today's session. Uh, Over to you, Paresh Patel sir.
Thank you, Khushbu madam and Gutanse madam, as well as dear students. Uh, Good morning, all of you. So previously we discussed about the how to prepare matrix representations for different symmetry operations, as well as reducible, irreducible representation, great orthogonal theorem, and with the help of the great orthogonal theorem, how to construct the character table. So yesterday we discussed about the construct the character table for C2B point group. Now let us start with the construct the character table for C3B point group. Now, how to construct a character table for C3B point group. Previously, we discussed about the definition of the character table. The devices can be utilized for the applications of the group theory and molecular symmetry is known as character table. Now, let us consider the character table for C3B point group. Let us consider the ammonia molecule, POCl3 molecule, as well as CSCl3 molecule. Okay. So construct the character table for ammonia molecule, construct the character table for POCl3 molecule, construct the character table for chloroform, as well as construct the character table for C3B, all are the same. So let us start with the construct the character table for C3B point group. Let us consider ammonia molecule. It belongs to E C3 plus, C3 minus, sigma Va, sigma Vb, and sigma Vc symmetry elements. It belongs to C3B point group. So we have to mention the this is the shape of ammonia molecule. Shape of ammonia molecule is pyramidal. Now in case of ammonia molecule consists six symmetry elements. Out of them, A is conjugate to itself to form a individual class. C3 plus C3 minus conjugate to each other to form a combined class. Sigma Va, sigma Vb, sigma Vc conjugate to one another to form a combined class. It means here numbers of the classes is equal to 3. So according to rule number first of the irreducible representations, numbers of irreducible representation is equal to numbers of the classes. So C3V E to YC3 3 sigma V. YE is a single, E itself conjugate to itself to form an individual class. C3 minus C3 plus C3 minus conjugate to each other to form a combined class, and 3 sigma V conjugate to one another to form a combined class. Now, numbers of the classes is equal to 3. It means numbers of the irreducible representations should be equal to 3. And we know that twice C3, 3 sigma V, A1, A2, E. 1, 1, 1. 1, 1 minus 1. 2 minus 1. This is the character table for C3B point. Now, according to the rule number first, numbers of irreducible representation is equal to numbers of the classes. Now, rule number second, or characteristics number second, the sum of the square of the dimension. Sum of the square of the dimension is equal to order of a group. And we know that dimension always corresponds to identity symmetry operation. Suppose this is L1, L2, and L3. So we can say that L1 square plus L2 square plus L3 square is equal to order of a group. Here, order of a group is equal to 6. Why? Numbers of the symmetry operations is equal to 6. So, order of a group is equal to 6. Now, this equation can be satisfied if the dimension of any two representations is equal to 1 and the value for third irreducible dimension of third irreducible representation should be equal to 2. Then and then this equation can be satisfied. 1 square plus 2 square is equal to 6. So, dimension for the 1, 1 and 2. Now to get the first irreducible representations, character for first irreducible, suppose this one is character 1 C3, character 1 sigma V. According to the rule number 3, the sum of the square of the character is equal to order of a group. The sum of the square of the character is equal to order of a group. It means 1 into 1 square plus 2 into character 1 C3 square plus 3 into character 1 sigma V square is equal to order of a group. But we know that to maintain the uniformity of the any character table, first irreducible representation with respect to 1. So if we take 1, then this equation can be satisfied. So first irreducible representations is 1 and 1. Now to get the values for the character of second irreducible representations, according to the characteristics number 4, any two irreducible representations are orthogonal to each other. So if we take T1 and T2, so 1 into 1 into 1 is equal to 1. 2 into 1 into 1 is equal to 2 character 2 C3 plus 3 into 1 into character 2 sigma V is equal to 0. Now this equation can be satisfied if the value for character C3 is equal to 1 and character 2 sigma V is equal to minus 1. Then and then this equation can be satisfied. So if we take 1 and minus 1, but it should be satisfied the characteristics number 3. The sum of the square of the character is equal to order of a group. It means 1 into 1 square, 2 into 1 square, 3 into minus 1 square is equal to 6. Means second irreducible representation should be 1, 1 and minus 1. Now to get the character for third irreducible representations, to get the third irreducible representations, first of all T1 and T3 and T2 and T3. According to the rule number 4, any two irreducible representations are orthogonal to each other. So if we take T1 and T3, so 1 into 1 into 2, 2 plus 2 into 1 into character C3, 3C3 plus 3 into 1 into character 3 sigma V is equal to 3 character 3 sigma V is equal to 0. If we take T2 and T3, then what will happen? 1 into 1 into 2, 2. 2 into 1 into character 3C3. 3 into minus 1 into character 3C3 sigma V is equal to 0. So 4 plus 4 character 3C3 is equal to 0. So character 3C3 is equal to minus 1. Now substitute this value in above one equation. 2 plus 2 into minus 1 plus 3 character 3 sigma v is equal to 0. It means 2 minus 2 plus 3 character 3 sigma v is equal to 0. It means character 3 sigma v is equal to 0. Now, to find out the Mulliken symbols, T1, T2, T3. Previously, what we discussed that if the dimension is one dimensional, then capital letter A and B can be used. If two dimensional, then E can be used. If three dimensional, T and F can be used. Okay. Here, this is one dimensional, and two dimensional. In case of the one dimensional, A or B can be used. Now, in case of A and B, when A can be used and B can be used, if the character for main principal axis is +1, then capital letter A can be used. If the character for main principal axis is -1, then capital letter B can be used. Here, this is one dimensional and the value for character C3 is +1. It means A can be used. This is again one dimensional and the character for one dimensional character for C3 is +1. It means A can be used. Now this is two dimensional, so E can be used. Now subscript 1 and 2. C3 and C3 is perpendicular to C2. C2. If the character for that C2 is +1, then subscript 1 can be used. If the value for character is -1, then subscript 2 can be used. Here, no perpendicular C2 axis is present. So we have to go for the next one. So here, the character for next one is +1, so A subscript can be used. Here, the value is -1, 2 can be used. Here, 0 means there is no subscript. Okay, so dear students, this is the character table for C3V point group, and exam point of view, this is most important. Either construct the character table for C2V point group or construct the character table for C3V point group. Dear students, always remember that construct the character table and explain the character table. Both are the different things. Construct the character table, it means we have to construct the character table. Explain the character table, it means we have to explain each and every terms involved in the character table. So next table is explain the character table. Or explain the different areas of the character table. C2V E, C2 sigma V X Z, sigma V Y Z. A1, A2, B1, B2. 1, 1, 1, 1, 1, 1, -1, -1. 1, -1, 1, -1. 1, -1, -1, 1. C3V E YC3 3 sigma A1 A2 E 1 1 1 1 1 -1 2 -1 0. Now with the help of this character table, we can write down the values of area number 4 and area number 5. So this is Z, X, Y, RZ, RY, and Rx. Similarly, x square minus y square, z square, xy, xz, and yz. Similarly, in case of C3 point group, z, rz, xy, rx, ry, x square plus y square, z square, x square minus y square, xy, xz, and yz. Okay, so with the help of this correct table, okay, it is allowed in our examinations. Clear? So with the help of this character table, we can write this character table for C2V and C3V. Now, explain the character table. It means we have to mention all the terms involved in this character table. This is area number 1. This is area number 2. This is area number 3. And this is area number 4. This is area number 4. Okay. Area number 2 represents Mulliken symbols. Before that, C2V, C3V. This is the left corner on the top of the table. This represents point group. Area number 1 represents different characters by operating different symmetry operation. These are the area number 1. This is the area number 1. This is Mulliken symbols. Okay, we already discussed that. If the dimension is one dimensional, then a capital letter A or B can be used. If the character for main principal axis is +1, then capital letter A can be used. If the value for character for main principal axis is -1, then B letter can be used. And if the dimension is two-dimensional, then E can be used. And if the dimensional is three-dimensional, then T and F, capital T and capital F can be used. Okay. Then subscript. We have to go for the C2 perpendicular to the main principal axis, and the value for or character for that perpendicular C2 axis is +1, then subscript 1 can be used. If -1, then subscript 2 can be used. Then if the value for sigma h, okay, there is no sigma h in both these character table, but in case of D3H character table, sigma h is present. So character for sigma h is +1, then single prime can be used. It means single dash. If the character for sigma h is -1, then single prime can be used, double dash can be used. It means A1 dash, A2 double dash, A3 double dash, etc. Now, in case of I is equal to -1, +1, then +1 and -1, then E and G substitute can be used. So these are the Mulliken symbols. Now we are going for the third part of the character table. Third part of the character table represents the rotation along the x-axis, y-axis, and z-axis, and when anyhow they corresponds to p orbitals, pz, px, and py. Okay, if we rotate the symmetry operation along the pz axis to give this irreducible representations. And last area or fourth area of the character table represents as a d orbital, or we can say transformation properties. Okay, this represents dx square minus y square, dz square, dxy, dxz, and dyz. Okay, so this is the explanation of the character table. So first of all, we have to give the definition of the character table. The devices can be utilized for the applications of the group theory and molecular symmetry is known as character table. Now we are going for the another title of our topic, that is application portion. In applications of the group theory in the atomic orbitals as well as bondings are in our syllabus. So let us start first with the applications of the group theory in the atomic orbitals. We know that x is equal to r sine theta cos phi. Y is equal to r sine theta sine phi, and z is equal to r cos theta. We can simply write against px is equal to capital R sine theta cos phi. Py is equal to r sine theta sine phi, and pz is equal to capital R cos theta. Okay, so with the help of this relation, we can find out the how many orbitals involved in the bonding skeletal of the molecules. So let us start with the first with the water molecule. Let us consider water molecule. It consists E, C2, sigma Vxz, and sigma Vyz. Okay. Now, how to find out the involvement of atomic orbitals in the bonding skeletal of the molecule? So, first of all, find out the symmetry elements are present in the molecule, and then operate different symmetry operation on the s orbital, p orbital, and d orbital, and find out the changes, and that changes can be represented as a bonding skeletal of the molecule. So let us start first with the s orbital. We know that the shape of the s orbital is spherical. Now, if we operate identity symmetry operation on the spherical shape of the s orbital, so there is no change, it means character is 1. Okay. If you operate C2 symmetry operation on the spherical shape of the s orbital, so there is no change in the spherical shape of the s orbital, so character is 1. Sigma Vxz. If you operate sigma Vxz symmetry operation on this spherical shape of the s orbital, so there is no change, it means character is 1. Sigma Vyz. If we operate sigma Vyz on the spherical shape of the s orbital, so there is no change, it means character is 1. Now, with the help of the character table, with the help of the character table, okay, so 1 1 1 1, this is nothing but the A1 irreducible representations, and here Z is mentioned. It means this is the character for contribution of s orbital in the bonding skeletal of the water molecule. Okay, so dear students, with the help of this character table, we can assign the contribution of s orbital in the bonding skeletal of the water molecule. Now, p orbitals. What is the role of p orbital on the bonding skeletal of the water molecule? We know that px is equal to r sine theta cos phi. Py is equal to r sine theta sine phi, and tz is equal to r cos theta. Now here theta remains unchanged, phi changes to pi plus pi. So first of all, if you go for the px, e into px is equal to e into r sine theta cos phi. By operating identity symmetry operation, there is no change. It means r sine theta cos phi is equal to px is equal to px. It means character is plus 1. Character is plus 1. Now, if you operate C2 symmetry operation on px, generally we consider any molecule on the z-axis. It means x is perpendicular to the z-axis. It means we have to rotate water molecules to pi plus. It means 180. So C2 into r sine theta cos phi is equal to r sine theta cos pi plus 180 or pi is equal to r sine theta cos phi cos theta minus r sine theta sine pi. Now we know that the value for cos pi and sin pi so is equal to minus 1. It should be pi. So is equal to sin pi is equal to 0 and cos pi is equal to minus 1. So minus r sine theta cos phi minus 0. So is equal to minus px. So if we operate C2 symmetry operation on px, it changes to minus px. It changes to minus px. It means character is equal to minus 1. So if we operate C2 symmetry operation on the px to give a minus 1. If we operate identity symmetry operation, so there is no change in the. Okay, next one is sigma vxj in on px is equal to sigma vxj r sine theta cos pi is equal to, if we operate sigma vxj, so I think there is no change in the, it is in the same plane. Px is in the same plane. It means there is no change, is equal to px. So px becomes plus x. Px becomes plus x. Px sigma vyz on px is equal to sigma vyz r sine theta cos pi plus pi is equal to r sine theta, sorry, cos pi is equal to r sine theta cos pi plus pi is equal to r sine theta cos pi minus r sine theta sin pi is equal to, value for cos pi is equal to minus 1, r sine theta cos pi minus 0 is equal to minus px, or we can say character is minus 1. So overall result is C2V E C2 sigma Vxz sigma Vyz. Character 1 minus 1 1 and minus 1. Okay. Second route is also possible. Suppose this one is px. If you operate identity symmetry operation on this px, this is px. By operating identity symmetry operation, so there is no change in the position of the lobes. If you operate C2 symmetry operation to change the minus and plus 1, it means here character is equal to plus 1, here character is equal to minus 1. If you operate sigma v x z, so there is no change in the position of the lobes. So character is equal to plus 1. Sigma v y z. So by operating sigma v y z plus and minus, it means character is equal to minus 1. So same results can be obtained by operating different symmetry operation on the lobes of the px. So 1, minus 1, 1 and minus 1. So with the help of the character table, okay, 1, minus 1, 1 and minus 1, which corresponds to B1 irreducible representations, So this is the nothing but the, this is x, means in the third column it represents as a x, and this is nothing but the B1 irreducible representations. So we can conclude that the contribution from px orbital, it is nothing but the 1, minus 1, 1 and minus 1. Similarly, with the help of this character table, y and z are there, so we can represent b2. This is y. It means b1 irreducible representations, that is the value for contribution from py e c2 sigma vxz sigma vyz. So this is the contribution from b2, 1, minus 1, minus 1, 1, and pz, this is nothing but the b2, 1, 1, 1, 1. This is the contribution from e1, or we can say pz. Okay. So what is the role of p orbital on the bonding skeletal of the water molecule, oxygen atom of the water molecule? So this is the contribution from px, this is the contribution from py, and this is the contribution from pz. So with the help of this character table, we can assign these irreducible representations. So this is the x-axis, this is the z-axis, this is x-axis, and this is the y-axis. So with this help, we can, this is the derivation for contribution from px orbital. Similarly, we can write the contribution from py and pz. And similarly, with the help of the character table, we can assign the contributions of d orbitals and the contribution from the orbital, that is dx1, b2, dxz, b1, dyz, b2, dz square, a1, dx square minus y square, that is contribution from a1. Okay, so with the help of this character table, we have to go for the area number 4, and with the help of this area number 4 we can write down this contribution from the orbital. So we have to prove the value for px, and then we have to mention the contribution from py and pz as well as d orbital. But we have to remember that the third column of the character table which represents p orbitals, and fourth column of the character table which represents d orbitals. So dear students, this is the applications of bonding orbitals, applications of group theory in the bonding orbitals of the s orbital, p orbital, as well as d orbital of the oxygen atom in water molecules. So exam point of view, this is most important whenever we talk about the transformation properties. So we have to mention that px, py, and pz, that is the transformation properties of p orbitals of the oxygen atom in the water molecule, and this is the most important questions. Now, what is the role of p orbitals in the combined p orbitals? That is we have to mention. If we operate px, py, and pz, okay, so if you operate identity symmetry operation on the combined p orbitals, so I think there is no change in the position of the px, py, and pz. So we can write the matrix representations for identity is equal to 1 0 0 0 1 0 0 0 1. Similarly, if we operate p1, p2, p3, c2 operation, so by operating C2 symmetry operation on water molecule. So there is no change in the position of the PZ. Why? We can consider the any atom, any molecule along the z-axis. So we can write Px as a minus Px, Py is a minus Py, and Pz remains as it is. So we can write the matrix representation is equal to minus 1 0 0 0 minus 1 0 0 0 1. If we operate sigma Vxj on Px, Py, and Pz to give by operating x and z. So Px is available in the same plane, Py is perpendicular minus Py, and Pz remains as it is because it is in the same plane. So we can sigma Vxj write the matrix representation 1 0 0 0 minus 1 0 0 0 1. So here character is equal to plus 1. Here character is equal to minus 1. Here character is 3. And last one, Px, Py, and Pz. If we operate sigma V Yz. So in case of the Yz, x is perpendicular to the Yz. X is perpendicular to the z. Px is perpendicular to the Yz plane. It means minus Px, Py remains as it is, Pz as it is. So sigma Vyz is equal to minus 1 0 0 0 1 0 0 0 1, and here character is equal to 1. Now C to V, E to IC3, 3 sigma V, P orbital, contribution from P orbital, this is 3-dimensional, minus 1 C2 sigma Vxz sigma Vyz. 1-dimensional and again 1-dimensional. Okay, so this is the contribution from total p orbitals. Before that, we already discussed about the contribution from px orbitals, py orbital, and pz orbitals. So this is nothing but the contribution from px, p orbitals as a combined px, py, and pz. Now, this is reducible representation. Why reducible? The value for identity symmetry operation is 3. So we can say that the contribution of p orbital is a three-dimensional. Now we can reduce this three-dimensional into 3 irreducible representations with the help of ni is equal to 1 upon h, character r into r, and character I into r. So with the help of the relation between reducible and irreducible representations and character table 4, C to B point group, A1, A2, B1, B2, 1, 1, 1, 1, 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1 minus 1 minus 1, 1. Okay. With the help of this, value for n1 is equal to 1 upon h. Here, the value for h is equal to 4. So this is reducible, and these are the this is the characterable, or we can say irreducible component. H is equal to 4. So 3, 1, 1, 3. Minus 1, 1, 1, minus 1. 1, 1, 1 is equal to 1. 1, 1, 1 is equal to plus 1. So overall result is equal to 1. So value for n1 is equal to 1. n2 is equal to 1 upon 4. 3, 1, 1, 3. Minus 1, 1, 1 is equal to minus 1. 1, 1, minus 1, minus 1. 1, 1, minus 1, minus 1 is equal to 0. So value for n2 is equal to 0. Now what about n3? 3, 1, 1, 3. Minus 1, 1, minus 1, plus 1. 1, 1, 1, 1 is equal to plus 1. 1, 1, minus 1 is equal to minus 1 is equal to 1. So value for n3 is equal to 1. n4 is equal to 1 by 4. So 3, 1, 1, 3. Minus 1, 1, minus 1, plus 1. 1, 1, minus 1, minus 1. 1, 1, 1 is equal to plus 1 is equal to 1. So the value for n1 is equal to 1, n2 is equal to 0, n3 is equal to 1, n4 is equal to 1. So total p orbital, we can write that is equal to n1 is equal to 1, a1, n2 is equal to 0, plus b1 plus b2. This is one dimensional, this is one dimensional, this is one dimensional. So dear students, prove that p orbital three different belongs to three dimensional, and as a combination of px, py, and pz as a one dimensional representation, prove it. So we have to operate different symmetry operation and combine p orbitals to get the reducible representation, convert this reducible representation into irreducible component, and this is thus p orbital belongs to three different irreducible representation. Prove it. So we have to mention this portion only. And whenever talk about the transformation properties of px, py, and pz, so in that case we have to derive the equation for px, and similarly we have to write the py and pz. So dear students, this is the applications of the group theory in the bonding skeletal of the molecule, atomic orbitals of the molecule. Now, last section of our unit is the applications of group theory in the bonding, particularly sigma bonding, is in our syllabus. Applications of group theory in sigma bonding. This is the last title of our topic. In this case, how to find out the sigma applications of the group theory in the sigma bonding. So first of all, we have to find out the different symmetry elements are present in a molecule, and then consider that atom orbitals in form of the vectors, operate different symmetry operation on these vectors, and find out the changes, and that changes can be represented as a reducible representation, and compare that irreducible component with the atomic orbitals involved in the sigma bonding, and with the help of the group theory we can predict the hybridization of the molecule. So let us start with the first molecule is BCl3 molecule. Suppose this one is size 1, size 2, and this is size 3. Now the hybrid orbitals are directed to the concerned to the trigonal planar structures. Now, three hybrid wave functions, size 1, size 2, and size 3, can be considered as a V1, V2, and V3. Now, operate different symmetry operation. We know that BCl3 molecule belongs to the 3H character table, and it consists E twice C3, 3C2, sigma H, twice S3, 3 sigma V symmetry elements. Now, if you consider V1, V2, and V3 and operate RNP symmetry operation on it. So there is no change in the position of the vectors. So we can assume the matrix for this 1 0 0 0 1 0 0 0 1, or we can say character is equal to 3. Character is equal to 3. Now if we operate C3 plus and C3 minus, V1, V2, and V3, if we operate C3 symmetry operation, okay, C3 plus, it means one time clockwise rotation. It means V1, V2, V3. So position of all these vectors will be changed. So we can write it V3, V1, and V2. So C3 plus can be represented as 0 0 1, 1 0 0, 0 1 0. So character is equal to 0. Similarly, in case of V1, V2, V3, if we operate C3 minus symmetry operation, so what will happen over here? V2, V3, and V1. C3 minus is equal to 0 1 0, 0 0 1, 1 0 0. So again character is equal to 0. So in this case, we can write D3H E twice C3, 3C2, sigma H, twice S3, 3 sigma V. So identity 3, it is 0. Now, in case of C2, V1, V2, and V3, if we operate C2, okay, so this is the main principal axis, and anyone can be considered as a C2. So if we operate C2 symmetry operation, the position of that C2 remains unchanged and other will be changed. So what will happen? V1 remains as it is. V3 and V2 will be interchanged. So matrix representations for C2 can be represented as 100, 001, 010. So the character is equal to 1. So we can mention that character is 1. Next one, if we operate sigma h. Sigma h means this is the sigma h. It means there is no change in the position of the vectors. So all the vectors remains as it is, v1, v2, v3. So matrix representations for sigma h is equal to 100, 010, 001. So character is equal to 3. So we have to mention as a 3. Twice s3. Twice s3. It means c3 plus sigma h. So already we discussed that c3 plus sigma h. Okay, if we operate c3, the position of all the vectors will be changed, and sigma h means as it is, means character is 0. Sigma v, by operating sigma v, this is one sigma v, second sigma v, third sigma v. Okay, by operating sigma v, the position of one vector remains as it is and two will be interchanged. It means position of, suppose v1 remains as it is, v2 and v3 will be interchanged. So character is plus 1. Now this is reducible representation, or we can say sigma. And if we compare, if we reduce these reducible representations, with the help of the character table for D3H, this is the character table for D3H, and with the help of this character table, we can reduce the values, and with the help of that, values for a n1 is equal to 1, n2 is equal to 0, n3 is equal to 0, and n4 is equal to 0, n5 is equal to 0, and n6 is equal to 1. It means we can predict that T sigma is equal to A1 plus E dash, A1 plus E, A1 plus E. And in this character table, it is nothing but the s orbital. This is the contribution from s orbital. And here in the second one, it is x and y. It means the contribution from px and py. And in the fifth column, dx square minus y square, dxy, dxz, and dyz. Okay, so we can mention that dx square minus y square, dx square minus y square, dxy, dxz, and dyz. Okay, so it is available in the in this character table. Okay, so we can predict that the contribution or contribution from hybrid orbital can be formed by either sp2 or sp2 hybridization. But we know that p is nearer than d orbital, so bonding orbitals in the sigma bonding can be formed by sp2 hybridization. This is the conclusion. So with the help of this group theory, we can assign the hybridization in the sigma bonding of any molecule. So second molecule is ammonia molecule. Ammonia molecule consists A C3 plus C3 minus sigma Va, sigma Vb, and sigma Vc symmetry elements. In case of ammonia molecule, CH1, CH2, CH3. The shape of the ammonia molecule is a pyramidal. We can consider a three hybrid wave function, three hybrid orbitals in form of the vectors v1, v2, and v3. Now, if you operate different symmetry operation on v1, v2, and v3 and find out the changes, suppose v1, v2, and v3, if you operate identity symmetry operation, so there is no change in the position of the all the three vectors. It means matrix for the identity can be represented as 1 0 0 0 1 0 0 0 1. So character is equal to 3. In case of v1, v2, or v3, if we operate either c3 plus or c3 minus, okay, this is the main principal axis. It means v2, v3, v1, or we can say anti-clockwise to give v3, v1, v2. So matrix representations for c3 plus 0 1 0 0 0 1 1 0 0. So character is equal to 0. Similarly over here c3 minus is equal to 0 0 1 1 0 0 0 1 0. So character is equal to 0. And last one is v1, v2, v3. If we update first sigma va, so v1 remains as it is, v3 and v2 interchange is equal to 1 0 0 0 0 1 0 1 0. So character is equal to 1. Similarly, in case of sigma vb and sigma vc, so we can write sigma v c3v e twice c3 3 sigma v t sigma v is equal to 3 0 1. So with the help of ni is equal to 1 upon h, character reducible representations, n character I into R. In case of ammonia molecule, C3V E twice C3 3 sigma V A1 A2 A3 1 1 1 1 1 minus 1 2 minus 1 0. As well as we have to mention third portion and fourth portion also. So here n1 is equal to 6 3 1 1 3 0 means 0 1 3 1 is equal to 3. So n1 is equal to 1, n2 is equal to 1 by 6 3 1 1 3 0 1 3 minus 1 minus 3 is equal to 0, and 3 is equal to 1 by 6, and 3 is equal to 1 by 6 2 0 and 0 is equal to 1. So T sigma is equal to A1 plus E. This is the contribution from S orbital. And in the second position, Px or Py. And in the fourth column, x square minus y square and z square dxy or dyz and dxz. It means in the ammonia molecule, sigma bonding can be formed by either sp2 hybridization or sd2 hybridization. But p is very nearer to the s orbital, so bonding orbitals in the ammonia molecule can be formed by sp2 hybridizations. So dear students, this is the applications of the group theory in the sigma bonding. So with the help of the uh, uh, group theory, we can assign the contribution from atomic orbital as well as bonding skeletal of the molecules. So I think this is the end of our this unit, and I tried a lot to explain the all terms involved in this unit. So I really appreciate the effort from KBS College. I thankful to the principals of the KBS College, Dr. Poonam Madam, as well as coordinator of this event, Dr. Khushbu Desai Madam, and other colleagues. So I'm also thankful to dear students. So thank you very much for giving me opportunity to share my views to the students. So thank you once again. Have a nice day.